Welcome AP Physics 1 to this lesson on vectors. If instead of this video, or in addition to, you want to do some reading, you can look at section 3.1 and 3.2 in your textbook. And to practice this stuff, look at homework packet 2, pages 3 through 6. In this video, we're going to specify vectors, basically describing them, naming them, talking about them, and then we're going to add and subtract them so that we can describe motion in not just one dimension, but in 2 or 3 as we go. To specify a vector, we need two things. We need its magnitude and its direction. And there are 3 different ways to do this. We can do it graphically, that's just drawing it. We can say a magnitude and an angle, or we can use components, the x and y and z, if 3 dimensions pieces of it. So to specify a vector graphically, you have to draw things to scale. This vector that is 5 meters long is, of course, longer than the vector that is 3 meters long, and then the actual direction they point is the direction we are talking about. It can be more helpful sometimes to use a magnitude and an angle. Vector Q here is 3 meters long, and it is at an angle of 150 degrees measured from the positive x, the way we deal with circles and angles. P is 2 meters long, positive 30 degrees. You can also use north of east, north of west, compass directions as you like. When we specify a vector, we can also use the component method. Instead of talking about the total magnitude, like 5 meters or 30 meters per second, we could talk about the x and y pieces of it. This vector A is 3 meters in the x and 4 meters in the y, 5 meters total. It forms a nice little right triangle. This is Mr. Graham's favorite right triangle, the 3, 4, 5 right triangle. We can go a little bit further with this and talk about how we would find the components. If I give you a vector, like this vector A, 2 meters long at an angle of 30 degrees above the positive x-axis, using sines and cosines, we can find the x and y components, or the various sides of the triangle. And we can say that this vector A is 1.7 meters in the x direction and 1 meter in the y direction. We can do this for any vector, but we do have to be a little bit careful about signs here, right? The x component of vector A is in the positive direction, 1.7 meters, and vector B, the x component, although the same length, is negative 1.7 meters. And that's true of sort of any vector. And if you look at the 4 different quadrants here, in the first quadrant, both x and y are positive. The second, x is negative and y is positive. The third, both x and y are negative. And in the fourth, x is positive and y is negative. Once we've specified vectors, we can then add and subtract them. Primarily, we're going to be worried about adding, but subtraction and addition are connected to each other. We're going to do this graphically, and we're also going to do this analytically. So graphically, you simply draw one vector after another. It's like following a treasure map. Go this many paces in that direction, then do that. We call this the tip-to-tail method because the tip of one connects to the tail of the next. So in this case, adding A and B, vector A is 2 meters plus 3 meters. Notice we go one and then the other. And then vector C, the resultant, is another way of getting from the beginning to the end of that path. You'll notice if we add vectors B plus A to get C, we get the exact same thing as A plus B to get C. We go around a different path, but vector C is the same regardless. This means that vector addition is commutative, meaning whatever order you do it in, you get the same thing. But it is not arithmetic, right? This is not just adding up 2 meters plus 3 meters to get 5 meters. That would be incorrect. That would only work if those vectors were along the same line. You can also use the parallelogram method, and this is probably something you've seen. This is kind of combining both of those graphical methods, B plus A along the dotted line, or A plus B along the dotted line gets you to C. You form this parallelogram, and the resultant goes along the diagonal. We can do this graphically as well. The big thing about the negative of a vector, or a subtraction of a vector, A minus B is the same as A plus negative B. And when you put a negative in front of a vector, all it does is change the direction. Notice that B and negative B are the same line, but the arrow is just on the other side. The direction reverses. So a little conceptual check here. If A is 10 meters due west or to the left, and B is 10 meters due north, A minus B equals C. Which of these is the correct diagram? We do A first, then we do negative B, resulting in option C. A plus the negative of B, so that's south, results in C. Another question is to think about: if A plus B equals B plus A for vectors, commutative property, is vector subtraction also commutative? Does A minus B equal B minus A? Well, it turns out that it does not, right? Here we have A plus B and B plus A on the left, A minus B and B minus A, giving us different C vectors. Notice that they're reversed of each other, so it's not commutative. You can't just do it in any order. If we're adding and subtracting vectors analytically, instead of having to draw them, if they're collinear, that means they're just in the same line, you can just add them up. 3 meters plus 4 meters equals 7, or the negative, 3 meters minus 4 meters is a negative 1 meter, right? That works pretty simply. But of course, vectors just in one dimension didn't really need all of this. When we're talking in 2 dimensions, there's a couple of scenarios, and this is our most common, that they're at right angles. We have something in the x direction and the y direction, 3 meters and 4 meters. These add up and form a nice right triangle. We can find the hypotenuse of that triangle or the resultant C using the Pythagorean theorem, and then we can find the angle using the inverse tangent. Again, Mr. Graham's favorite triangle, the 3, 4, 5. If the vectors are not at right angles to each other, we have to take an extra step. First, we have to find the x component of A, the x component of B, and add up the x components to get the resultant for C. Then we do that in the y direction for A and B and add them up to get the y component of C and recombine. But hopefully you notice that this is the same as if we did it graphically. A plus B gives us C. Right? So the method kind of laid out for you is resolve every vector into its components, x, y, and sometimes z. Add all the x components to get the x resultant, add all the y components to get the y resultant, and so on. Keep track of signs, and once you've done all of that, you can put them back together. So a little example here. If we have vector A, B, and C, so this is kind of a direction. You drive 50 kilometers east and 30 kilometers north, then 100 kilometers, 30 degrees south of east. We're going to find all the different pieces. You find the x component of A, B, and C, so that's positive 50, 0, and positive 87 kilometers. You find the y components of A, B, and C, 0 kilometers, positive 30 kilometers, and negative 50 kilometers. And then you add them each up. And once you have those two components, positive 137 kilometers in the x and negative 20 kilometers in the y, you can put them back together to find a resultant triangle, which looks something like this. Pythagorean theorem to find the hypotenuse, and then the angle can be found with inverse tangent. So last little question here, right? If you were to take vectors 1 and 2 and add them up, right, what are the signs of the x and y components? Well, if you add them directly, as shown here, we'll get negative in the x, positive in the y. If you subtract 2 from 1, you'll get negative for both. And if you subtract 1 from 2, you would end up with positive for both. That kind of wraps up the examples. Again, vector practice is on pages 3 through 6 in packet number 2.